Notice that this always comes in ratios, all right? So, I don't know what I called it. I call it gamma or something. I don't remember what I called it. My algorithm doesn't need gamma. All right. So e to the gamma is just a normalizing factor. All right. That's a beautiful thing about the Langevin diffusion. Well, I could maybe not know. I could, if I had p of this form. If I look at a ratio of p of y over p of x, it's going to be just the ratio of exponentials. The gammas are going to cancel. So Langevin doesn't need, or I should say Hastings Metropolis. Or Metropolis, Hastings, flip it around, I don't know, whatever you like. So both of these, both Langevin and Hastings Metropolis don't require knowledge of normalizing constants. And that comes up in statistics a lot. A lot of times you know the distribution up to a normalizing constant. And and computing this is numerical integration. You got to integrate this over Rn. Okay, so back to your point. I'll draw it here first. So what are we going to? What's our choice going to be? A typical choice is this. I'll just write a little xt there. So I've got an xt here, and let's look at the Metropolis sampler, which is the most popular, way more popular than the independent sampler. And let's think about how this actually works. So the way it works is that I'm given, I'm going to put the t in there just so we can remember what it is. So I observe that, and what's yt plus 1? Well, yt plus 1 is distributed according to this distribution with, Put a little dot there. I've got a density or probably a mass function where the variable is right there. If I put a y there, it'll be confusing, right? Okay, so for discrete state space, the probability yt plus 1 equals y would just be q of y minus x. What is that? What's yt plus 1? How would you write that down? See, I've shifted the mean to be xt instead of 0. Because it's symmetric, the mean is 0. So what's happening really is that yt plus 1 is equal to little xt, which is big xt, plus, say, wt plus 1, where w is an ID sequence with parameter q, with distribution q. So I'm just taking my current state, adding on some noise, typically Gaussian. That's a typical thing people will use. So if it's not discrete state spaces, it's usually continuous. And you just add on some noise. So how would you do that in this example? So let's say that this is 12, and this is 22. How's that? I don't know. Just to get a feeling of scale. what would you choose? Large variance? I don't know. Good question. Maybe. Yeah. Yeah. That's interesting you'd say that. Remember, we get to move. You know? Yeah, I agree with you for the independent sampler. For the independent sampler, we might have to sort of cover the whole distribution possibly. But we get to keep moving. You know? So it's no, I don't know. I'm surprised. Most people would think of small variance, wouldn't they? That you wouldn't want to jump. See, because we don't want, given that the new proposed value is xt plus a Gaussian, we don't want to be knocked out of the park. So I think most people would presume it would be something intermediate. So if this is 34, this is maybe 3, you know? So that's a standard deviation. So maybe N09, you know? Maybe, you know. Yeah. 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 So I wish I hadn't put it there. Let's see. I wish I hadn't put this so close to a maximum. Let's say we jumped over here. All right. So right here, this is a maximum. So what I wanted to say isn't going to apply very well. Suppose I actually accepted the next transition and ended up here. What's going to happen next? Well, I look up here, and I'm going to be looking at ratios of probabilities. All right. So whenever my proposed guy is bigger than my previous guy, I'm going to say yes. So I always want to go uphill. Right. So if the new guy is over here, if the new y is here, I say yes. Over here, I say no. I mean, with some probability. There's a ratio here. Maybe there's probably a half that'll accept it. All right. So what happens is, if you actually sample this maybe with not sigma w equals 3, but sigma w equals 1 or less, it tends to sort of drift towards the local maximum and get stuck, like you say. You know, because it favors, you know, if the ratio is bigger than 1, you say yes and accept it. Right? And it doesn't like going downhill. So if you actually simulate this, you'll see it evolving with a small variance. You'll see it evolving here for quite a while, and then making a transition and evolving here for a while, and making a transition here. And if you simulate the Langevin diffusion, you'll see the exact same thing. And that's because they're related. It turns out that you could approximate this by Langevin diffusion, if this is small. Yeah. Yeah, but so it's not so bad. You know, you basically have to choose your variance here, which is somehow related to the standard deviation when you have a multimodal distribution like this.
But if you have something like that, and that's okay because you want
Yeah. Yeah. I mean, but in multi-dimensions, you know, who knows, right? And that's the thing. In high dimensions, you know, there's no cookbook. Yeah. Yeah. But you're right, you're definitely right. So if you take a small variance, you're going to get stuck here for a long time, jump over here, get stuck here for a long time. If you have a high variance, what goes wrong? You'll reject a lot. So if you have a high variance, I'm here, I'm way out here, and this is 0 practically. And I do another thing, it's way over there, you know, P of y is tiny, reject, reject, reject. It starts looking at an independent sampler. That's the thing. So it's, yeah. Yeah. So you could code this tonight, right? Yeah. There's so many things to say.
Can I ask a question?
Yeah.
Yeah, so if AXY doesn't depend on the proposal distribution, how do you choose the proposal distribution?
Oh, that's what I was just talking about.
Yeah.
You know, I mean, so basically, in the case where the typical, very typical case people use again is where this is, again, density is not discrete. You choose this to be Gaussian, with just a identity covariance matrix. And the whole goal then is to try to choose the variance properly. And you want some intermediate value. If it's very small, you'll sort of get stuck near the local maximum density for a long time because it tends to move uphill. I mean, take a look again. We accept with probably 1 if the new probability is bigger than the old, right? And so we tend to crawl uphill. And so we're here for a long time, and then we go over there. And if you make the where'd it go? Yeah, if you make the variance of W massive, then you're shooting out far away. And so P of Y will be very, very small. So probability of acceptance is small. Yeah. And so you'll just reject. It's interesting. I mean, you've got these two extremes. Again, with high variance, you reject because you're thrown far away from where the density lies. So P of Y is small for many, many samples. And if you choose a very, very small variance for W, then because of this formula, clearly you don't move very far, and you crawl up towards a local maximum from this formula, Whenever you're bigger, you accept with probability 1. And so it takes, for the very, very small variance here, you live in one region of attraction here for a long, long time, and then you jump over here for a long, long time. And if you look at the Langevin diffusion, it's just what you'd expect. It really helps intuition. I mean, they're related. There's no way outside the course. It's way outside of any course. But it turns out there are papers out there saying that algorithm that we talked about over there, at least when the variance of W here is small, when sigma W is small, that this algorithm and this algorithm are related. And you all can imagine a gradient flow, I've got minus the gradient of U. If the density looks like this, then minus its log looks like that. And without any noise, you would just shoot down to a local minimum and stay there forever. And so if you actually watch the process evolve, this process or the other process, you go here for a while, shoot over here for a while, shoot here for a while. Okay.
So with this acceptance idea,
Yeah.
This algorithm really holds its weight, or water.
This is all there is.
Like in multi-dimensions.
It's all there is.
Multi.
That's all there is. I mean, it's a big research area.
Big vectors.
But this is it. I mean, this is, there are all sorts of tweaks to try to improve this. And there are adaptive techniques to try to tune parameters on the fly. And there's ways to reduce variance by other means. But this is the way that we sample from a target distribution.
So this is
it.
sampling like Kalman filter is to filtering.
Yeah. Yep. Metropolis Hastings to simulation is like Kalman is to filtering. No question. Yeah. Yeah.
So I go back to, I guess, the naive question. We still have to know P in this case.
Yeah.
Right? So,
Yeah. We have to know P in this
the
case.
reason we want to do this entire process is to have, it's not using this.
Yeah, that's the point. Exactly. Yeah, the point of this is that you've got some nasty P, and you either do numerical integration or you do this. That's right. But I think there's time to give you an example where you don't know P.
Repeat that last point.
That there's the time to give an example that's where you don't know P. No, what was the point again?
I missed the question.
A question was missed.
I just asked if you have to know P in this case.
Yeah. Yeah, so you definitely have to know P. It's right there. All right, one more application this time. One more application. So I gave you the independent sampler. I don't think that's used much. I think this is by far the most common approach. There's one more that's very popular For reasons you'll see why. So that was 1, 2, here's 3. All right, here's one example. I don't even know P. And I'm going to break my rules a little bit. So I've got it might be a density, might be discrete. Let me just think about densities for the moment. Again, it doesn't matter. All these algorithms look at ratios, and this can be a probably mass function of density, as long as it's consistent. That's all you need. So I don't know P, but I know it's conditional distributions. So what I know is this. So I know x of I given all the rest of the variables for each I. This is data that's given to me, and typically it's simple. And the typical way that people think about this is when you have what's called a Bayesian network. So what the graph is supposed to represent is how random variables influence each other. So it's a generalization of a Markov chain. So basically, the distribution of, say, x4 given everybody else Okay, so when I write the probability of xi density or discrete doesn't matter, given everybody but myself. Okay, so if we take the case of the fourth variable here, the probability of x4 given everybody except 4, right? The graph is supposed to represent that only depends on 7, 6, and 3. I'll put these in order. All right, and really I should write x4 given. It's the notation would kill me if I put all the details in. Normally you would write capital X4 condition on x4 minus, all right? Because this p is different than that p, all right? But I just can't put all that notation in. Nobody does.
Is this a spin-off on the Markov property?
It's a generalization of the Markov property. So Bayesian network is a spatial sort of Markov property, where for any node in the graph, given my neighbors, I'm conditionally independent. I'm conditionally independent of everybody else, given my neighbors. So it's it's a Markov random field. And so what you can do then is I know these, and I use those for proposal distributions. A couple of you have seen this before, because I can tell by the looks in your eyes, but bear with me. So what you do is, my proposal distribution is incredibly degenerate. So unlike this, where I'm like adding Gaussian noise, here I'm only going to perturb one entry at a time. So again, there are n nodes, and for j equals 1 to n, I have this distribution. Okay, it's very hard to write down, but very easy to say. My proposed new sample, I'm going to freeze all the other variables to where they are, but I'm going to change the jth one according to p, the real distribution. So here there's nothing to choose, we just take the real statistics. All right? Now, I'm cheating here because before I said I'd have one k, not a sequence of k's. But this gives rise to a non-homogeneous Markov chain, a periodic Markov chain. You know, there's going to be a t there, unfortunately, but this is cyclic. You're going to keep doing this over and over again in the circle. So when you're going to go, you know, for j equals, this is going to be a periodic. You're going to do this for 1, 2, 3 up to n. Then you're going to reset the clock 1, 2, 3 up to n, and so forth. So if you define a new process, which is, say, phi t is xt minus 1, xt minus n plus 1. So you look at the history over n samples, and a clock, which is just, no. You've all seen clocks. Basically, if n equals 12, hour 1, hour 2, hour 3 up to 12, and 1, 2, 3, that's a clock process. It's a periodic orbit. That is a time homogeneous Markov chain. And it satisfies these detailed balance equations. So basically, it is a, it is one of our friends. Because, basically what you do, instead of looking at the x process, you're looking at this whole phi t process. You look down at the clock, you find out what j that corresponds to. Then you say, oh, I'm going to change the jth, every xt is a giant vector, right? So all this is garbage anyway. So I'm going to perturb the t guy and take its jth coordinate and perturb it according to that distribution. So this whole big monster is actually a process generated by the Hastings-Metropolis algorithm with a very, very special proposal distribution, which depends on the clock, and then the clock is j. You look at the jth entry of the top guy. Because you can't change the past. I'm going to look at the xt to xt plus 1. And if you look at the acceptance probability, guess what it is? It's not as bad as it sounds. We just plug in and everything cancels out. So, you know, kx to y, or y to x, oh yeah, I just realized it. Hold on. So here I go to x minus j, because that's the data that was given to us. But these guys are equal, so I can go ahead and replace the x minus by y, j minus, it doesn't matter. And I just realized that the j minus is a bit fishy. We usually write minus j, sorry about that. It doesn't matter, but I just mean the vector with everything, with the jth end excluded. And what am I going to do now? Just, that looks like Bayes' rule or something. What is that conditional distribution? It's the full distribution divided by the probability of that. It looks bad, okay, but Bayes' rule says the conditional probability is the joint probability divided by the probability you're conditioning on. And you see I get a cancellation of P of x and P of x, and a cancellation of P of y and P of y, right? And what's left is I end up getting a ratio of, I get a minimum here of 1, and P of y minus j over P of x minus j, and that is, you know, because we don't change those guys. At each entry, we're only perturbing the jth element. So we accept everything. So the reason for all this work is just to embed the Gibbs sampler, that's what this is called, into Hasty Metropolis. So this is called the Gibbs sampler. So this is a standard algorithm, you know, and what we showed is because we can embed it in the Hasty Metropolis framework, it's a reversible Markov chain with, I mean, this is a reversible Markov chain, periodic as hell because of the clock process. A reversible Markov chain with the desired target distribution, and we always accept, there's no, because the Gibbs sampler doesn't have an acceptance probability. And so, so this answers your question. There are cases where we can do this without knowing P at all, right? Because it looked like we needed it, because in acceptance probability, we have a ratio of P's, but the ratio is always 1, so it's gone. So it's really cool. And so this is a workhorse because, you know, pretending that you have this conditional independence structure is really useful for models. You know, I mean, and then people want to do inference on this. They want to know the probability of something happening here based on observations there, and you need to compute these expectations, as you will see over the next 4 weeks.
It always says like it's a sample, like it's not really a test, right?
No, the test goes away. So the Gibbs sampler, because this is always 1, that's why if you look up the Gibbs sampler on Wikipedia or some statistics book, they will never mention acceptance. It's just, you just go through and you generate where to go. you just generate this Markov chain, by perturbing one component at a time. It's really pretty cool. Yeah. It's amazing you can get away with that. It's amazing you can get away with with just doing this by cycling. Basically, I take everything. I take X. I take everything but the jth component. I just perturb the jth element using this conditional distribution, and then I move down to the next to j plus 1 and keep doing that. That this resulting Markov chain is ergodic and has the right steady state distribution. It's amazing. It's absolutely amazing. And there's just a simple proof of that. A simple proof of
What
that.
sort of like guarantees do you have though?
Guarantee of what?
Guarantees of, I don't know, you tell me.
No guarantees of what? Yeah, what are the questions? Oh, yeah, you tell me.
Like if I was going to use this, right, to build up a sample distribution.
Yeah, it always works. Basically, I gave you a condition for irreducibility. You need the proposal distribution to be positive everywhere. So if it gives, it's nothing to talk about.
Like every sample I bring in, it's going to be a valid sample. Like it will.
Oh, well, yeah, let's go back to this. Yeah, that's a good question. So let's wrap it up with how you actually apply this, and we'll stop. Okay, so now we've got a machine to go and draw samples from a Markov chain. Okay, this is what we're claiming, that I can take the sample path averages, XK's, Gibbs, independent sampler, whatever you want, and be done with it. Well, we do know this will converge under the mildest of assumptions. It's going to be Foster's criterion or whatever, those geometric ergodicity conditions hold under really general conditions. So the law of large numbers holds, but let's just check the bias. So I didn't put this on the exam, I decided just to give you a break, but now we'll write it down. This is 1 over n summation k equals 1 to n of p, I heard it? I heard. What's missing? Yay! All right. So we do have bias, because this is going to converge to the steady state mean. We do know that under the conditions that we're going to always have, this will converge to pi of f, to expectation of fx. And typically geometrically fast. I can promise you that, okay? Even the density case, all of that, it's going to happen geometrically fast. So Langevin diffusion is the easiest to prove really mild conditions under which this converges geometrically fast. But how fast? That's the mixing time question. That could be really long. So k could be huge. But that's nothing. The bias is nothing. It's geometrically fast. And the bias is not the issue. The issue is the variance. The issue is the variance. So so there's some bias, but it goes to 0 quickly. Again, the variance is a problem. And that is a question for another lecture. But anybody think that that's the variance? Anybody thinks that that's a variance of f of xk? I want you to think about this, okay, over the next 48 hours. You know, the variance of this, we're talking about taking this monster and squaring it, right? Remember what the variance is. It's by definition the expectation of f hat n squared minus the expectation squared. That's the variance, right? So we're taking the whole monster sum and squaring that, right? And remember how the dynamics went. We stayed still with some probability. You know, we draw according to this distribution, and we either stay still or we move forward. And so you can imagine there's a lot of dependency between these two guys. And so we can't take the expectation of this estimator squared and think everything is going to cancel out. So this thing is typically much, much, much greater than the variance of one guy. Okay, but we'll have to see it next time. And that's the damn problem. You know, it's the mixing time. People obsess with that because it's a crisp, clear thing to try to get a handle on. But what the practical question is that, and that's people don't talk about it enough.